Okay, I hope everyone is hearing me clearly and also seeing my screen. Please let me know if there was something small or like the voice was not very clear. Uh, so I'm very happy that I have the chance that demonstrate our tool to ROS people. For people who we haven't met probably before, I'm Nima Rahimi Forushani, PhD student at KU Leuven. My supervisor is Bart Jacobs, who should be in this meeting as well tonight. I'm
Yes.
not sure.
Hi.
Oh, okay. Hi. Um, so basically, what we are trying to, what is the problem we are trying to solve? So we all know that ROS type system has nice memory safety and data rest freedom guarantees as long as you're just using safe parts of the ROS. We have extended our tool VeriFast to check that if in presence of unsafe code, those guarantees still hold. Uh, so let's look at the tool. Uh, Basically, tonight I decided to present the tool from the user's perspective. So there will be no slides. Please feel free to stop me anywhere that you had a question or you felt that something has been mentioned quickly. Uh, this is very fast. Very fast verifies programs using modular symbolic execution. And what is this? Let's consider this example program. Uh, so one way to verify that does this does something go wrong during executing this program is that just start execute it concretely. And when we encounter some line like this allocation line that gives us non-deterministic values, we can branch our execution for all of the possible concrete values that allocator gives us and continue all of those branches, which is practically impossible to do. Uh, but fortunately, if we look at alloc documentation, it says us it says us that it either gives us a non-null pointer, which means that the allocation has succeeded and we have a memory chunk, or it gives us a null, which means that the allocation has failed and we don't get any chunks. So basically, we can have, instead of infinitely many branches, we can have two branches here. One representing executions that allocation fails, and one representing executions and that allocation has succeeded. And instead of uh, keeping track of concrete values, abstract those details away and use a symbol instead of those values, and also keep track of the knowledge that we have, uh, we get about them during the execution of program in each branch. So in VeriFast, we can see that we can see our symbolic store, which is here. Uh, just to make sure everyone sees my cursor, most cursor. Okay, perfect. This is the symbolic store. It's mapping from variables to symbols. Here we see that there is a symbol P0 map. P is mapped to P0. Uh, Here, the assumptions component is tracking of the knowledge that we have gained about the execution. For example, we see that here we are in the branch that P0 is null, so we know that the allocation has failed, and Here, VeriFast tracks of the resources we have in this current execution path and the step of the program that we are in. So resources are like, for example, a memory chunk. Here, because the allocation has failed, we didn't get any memory chunks. Basically, our symbolic heap is empty. If we go ahead, we see that when we get to the reference line in the execution path, that the allocation failed, VeriFast catches the problem, complains no matching heap chunks, because when you dereference a pointer and write to it, you need to have a full chunk of the memory a pointer points to. So let's solve this. So here I add this check that if the allocation failed, I simply just abort the program. And now we see that the branch that allocation failed, well, reached end. But here in the other branch that allocation was successful, we are seeing that we are now in the end, at the end of the function. And we see that in this branch, P0 is not null. And we see that, yes, we have like memory chunks. But what happened is that at the end of the program, we are still having some chunks remaining in our symbolic heap, meaning that the program is simply forgetting about them, and they are leaked. So here, VeriFast complains about leaking heap chunks. Here, if I add the dealloc function and I unallocate basically free the chunk that I have allocated, this function gets verified and there is no more problems with it. Okay, so we saw how symbolic execution works and also different parts of VeriFast window so far, and also we saw the symbolic execution tree of our main function. Let's extend this example a bit more. So I'm going to use this allocation example and write a naive approximation of box library of the standard library. So it is like rather contrived because it's like wrapping on a raw pointer, and all of the functions are also unsafe functions. So, but we will build up toward a safe abstraction. So we see here that this new function is quite similar to the main function we saw earlier, and then at the end, instead of like just the allocating, it puts the pointer into the box U8 struct and returns it. From the previous example, we can see that, okay, there isn't a problem of showing undefined behavior here. But okay, let's say that we executed symbolically this function, and then at some other point of program, we encountered a call to that function. So again, if we naively execute the body of the function in the call side, there are many problems here. First of all, in presence of recursion and loops, or verification algorithm might not terminate. And also it's really, really inefficient. So what we do here is that we make symbolic execution modular as well, meaning that we ask user to write a contract for each function, and then we verify the body of the function, given that the required clause of the contract is provided, and at the end of the execution of the body, the ensures clause should be
It didn't.
satisfied.
We kind of just decided the other day that it was probably a no go. There's this. I don't know. There's a couple. There's a couple people that I'm like, you know, maybe I would want to go on a date with them. We'll see. I don't know.
Here. Yeah, okay.
Sorry, was that a question? I'm not sure.
I think that was an accidental unmute.
Oh, okay.
Sorry, go. Yeah,
Okay.
I wasn't sure. Yeah, sorry.
Okay. So very well. Let's look at action here. That how we verify this body against this contract. Basically, we learned that we saw in the main function, we saw earlier that we don't need any resource to begin with. We just want to allocate something, allocate memory and write our value there. So we don't need anything at the beginning. So basically this function requires nothing. And I have written these contracts and I'm changing them from comment to annotation to save some time that would be taken by typing. So, and then I expect this function that after it returns, it gives me a chunk, a memory chunk for this field of the struct. So, which returned by the function new. So result is a binder for the return value of the function. And this field pointer, we need a point to chunk to a value of this field. I expect that after this function returns, I will get this point to chunk for the field. And I also expect that get this other resource alloc block, which tells me that there has been a memory block allocated in heap at this address and with this layout. Because we are allocating U8, we have this layout of U8 value here, and also some other information about the pointer provenance, which I will not going to dig in. Here the function is quite similar to the main. We do the allocation, we abort if the allocation fails. So we will have the, basically we will have the chunk at this point in the successful allocation branch. It writes, we put the pointer here, and at the end of the execution of function new, yeah, at the end of the execution of function in successful branch, we see that yeah, we see that VeriFast consumes the ensures class of the function, meaning that after the execution, this function should provide these resources that has been mentioned in the contract. So, which we see that when it checks and consumes these chunks in the symbolic heap, these chunks are all provided. Okay, so if we check
I
this
think there's a
file,
question. Sorry, I think there's a question from Sasha who says, how are things like std alloc layout new U8 resolved? Is it a predicate defined somewhere by hand, or is it inferred automatically from the code of layout new? Do you check that new indeed returns this value in the spec?
so std alloc layout new is a fixed point, which basically gives you, let me actually read the rest of the question. Is it predicate defined somewhere by hand, or is it inferred automatically from the code? Oh no, so yeah, it is a fixed point, and we have like basically uh, axiomi axiomization of a standard library, and in that part, when you alloc something by a layout of some type, then again this alloc, you get this alloc block with a layout of that type, which basically what this thing fixed point gives you is a layout which its size is U8 and its size of U8 and its alignment is alignment of U8. So I can show you here Control F. Yeah, just a fixed point function that returns this. I hope it answered your question. Okay, so we check that the body of this function satisfies its contract. Now, when in a caller we encounter the call to that function, we do not execute its body. We just basically execute. We want in the call side we grasp the uh, effects of the call to this function by checking its using its contract, meaning that we consume the requirements of the function that is called, and then we produce the ensures contracts of the call. So we will get the effects of calling of that function. So here we made our execution or symbolic execution modular as well. So far, so good. We can, yeah, so there is basically, this is this is verified actually, but there is a problem here that if you look at these contracts, we see that they are leaking a lot of information about the internal of the library. What is this basically, that are this private field and etc. So we might want to make contracts more abstract. Also, it's cumbersome to all type all of these assertions every time. To make it, to solve this problem, we have this concept of predicates in the VeriFast. Yeah. So basically, I define a predicate box U8, and it gets some parameters, and then I write the assertion that I want to be the definition of predicate here. So I'm saying that having a predicate of BU8 with a value of this struct B and a value of U8 means that we have this points to chunk, and we have this alloc block, and we have this provenance information. And then instead of repeating these all here, we just say that, okay, new ensures to give, when the new returns, it gives us a box U8, which these value with these values as its arguments. What happens at the end of the execution of new here? We said that at the end of the successful path, then VeriFast tries to consume the ensures class, which is box U8. However, we saw that here we just have these bunch of resources and knowledge. We knew about this piece of knowledge. The fact that in VeriFast, moving from the predicates to their definitions and and the other way is manual. So you should basically use commands like open and close. Basically, I can write it here. What did go wrong?
You have to put R.
Oh, okay. Sorry, I didn't return the. Yeah. Okay. But in this case, because this predicate is precise, VeriFast tries to automatically close it, and it succeeds. I'm not going to dig into the preciseness and why is that, but it is like it's the automatically closing and opening the predicates is like not guaranteed, but sometimes it saves you some annotation and typing. Okay, so here we also made our contract more abstract, and we also can again call it. We see that we did use this same predicate in the drop that basically just opens the predicate, and again it is precise, so it is a VeriFast successfully opens it, and then deallocate just free all of those resources, and then at the end there is nothing to needed to be ensured by this. Okay, we have an unsafe version.
Sorry, I have a quick question about this precision thing. In practice, how often are your predicates precise? Is this kind of optimization that you get here in terms of like annotations? Is this something that you get to use a lot, or is it really for like edge cases?
No, basically, actually, I have used it a lot because like the predicate is precise if okay, I am going to explain that the predicate is precise if for the same input parameters it gives you the same resources and the same output parameters, and not all of the predicates are precise. It happens. So basically, when most of the time we are dealing with like memory resources or like ghost resources that they are all precise, and so we can basically use a lot these precise predicates. But the shortcoming here is that VeriFast does not always try to automatically open and close them, especially if they are like more complicated forms of predicates, for example, like predicate constructors, and so if you are familiar with VeriFast, you know predicate constructors. But yeah, maybe it's not the time to go on. Does that answer the question?
Yeah, absolutely. I was really just kind of curious about how often, like, you answered it as well, but I was just wondering like how often you would be able to leverage this in real world development.
Yeah, it helps quite. Yeah, especially when you get a bit fluent with VeriFast, you could get some good use of it. Very well. So we all know we made our contract abstract. And actually, we don't need to have this approximation of bugs just for a concrete type U8. We can also write it for a generic, in a generic form. So here I can show you the generic form of this unsafe box. All of the functions are still unsafe. Basically, the predicate is not different here. It's just instead of a points to a U8 value, it's a points to the generic value. And the allocation block is also allocation block for a generic layout. That works with the same principles. There is a exception here that earlier we were just allocating a single U8, so 1 byte, and it was and we were also writing just one U8 on it, so we didn't need to convert our chunks. However, here this allocator gives us a bunch of bytes with the size of this type T. Yeah, and then when we want to write on the memory, we should basically maybe people like transform this bunch of like array of bytes to a points to chunk that satisfies the properties of a chunk for the type T, and this lemma from U8s with the pointer of the type star muted T does that work for us. So if I continue stepping through my program, it takes the bunch of bytes and gives us a points to, and then we write on this points to, so the value gets updated here, and so on. Here in the drop again, we go the other way. So
yeah, excuse me.
Sure.
I was just wondering, why is there a requirement that type is more size more than 1 on the new function?
Oh, sure, because earlier the U8 we know that its size is not 0, it's 1, but with type T, the documentation of global allocator says that allocation for a layout of size 0 is undefined behavior. And
Okay.
if we don't have this, then the precondition of the allocator will not get satisfied, and the allocator, and basically it stucks here, complaining that.
Okay. Okay. Interesting.
Very well. Was that the only question?
I actually have a question about that.
Sure.
I mean, I guess I'm a little bit confused because how do you handle something like box new where T is a ZST? I mean, that's from
What
the
do you
spec.
mean?
At least I can create a box. Like I can create a box in Safe Rust for a ZST, right? Like there's nothing.
Yeah, but the thing is that I am using like allocator dielectric here. It's not exactly box.
Okay. Okay. Right. Yeah.
Yeah, I mean, real box
so I
says
guess
an if size is 0, then do
that's what I
dummy
was.
thing,
Okay.
else do this thing. So
Okay.
Yeah,
then you
Yeah,
wouldn't
that's
need
what
the
I was wondering.
it's
Yeah.
precondition.
It's
Yeah.
just a very simple version, like mimicking
Yeah,
that. It's
okay.
not real. Okay.
No, that's fine. Yeah.
Okay. Very well. So and for the drop version, we have like the other way as well. So we get the box of predicate here, and then for the allocation, we need to change it back to the like array of bytes to give it to the deallocator. One thing here, there's a problem here that this value of t might have drop destructor, and we are basically not destructing v, which means that we are kind of leaking v, this value. We will leave it like this here. Later, we will solve it in a safe abstraction. Okay, very well. Here we got this generic approximation of like this generic unsafe Rust, which verifies regarding these contracts, and so far so good. Now, if we looked at what we have achieved, we see that we have verified a bunch of unsafe, purely unsafe libraries against contracts that we provided, and we haven't used the nice information that Rust types are giving us. Basically, we should keep the unsafe footprint as small as possible and hide it under libraries that their interface is safe, so safe abstraction libraries. And we don't want to write these contracts, at least for safety verification, for the safe code as well. So the solution here is made by the Rustbelt project and Rustbelt paper you can look at. I'm not going to dig in to the details and the theory of Rustbelt. It's others people work. There is plenty of nice material and a very nice paper about it. We are just using what they have achieved, axiomatizing it here to verify that a safe abstraction actually does not violate type system guarantees. What we just need to know about Rustbelt here is that Rustbelt gives an interpretation of the types of Rust and tells us that if you give, you provide an interpretation for your type, which satisfies some structures you will see later. And then all of the methods of the which are the as the interface of your safe abstraction library, all of the public methods satisfy their signature type, then Rustbelt guarantees that, okay, your library will not violate Rust type system guarantees, and then a user of your library that just writes safe code can simply forget about the implementation of your library, and the fact that type checker type checks the user safe code against the interface of your library means that the user is good to go. So how do we ask our user to provide the interpretation? Again, this is following the Rustbelt approach. So a type interpretation consists of basically 3 components. We want a user to provide 2 of them here in VeriFast. Let's first start with the own component. So in the own component, I should define what basically does mean to own exclusively a value of my type. And this value, the meaning of this value can be dependent to the third to a third identifier as well or not. So this is basically this own component of the interpretation of our box, generic box here has a thread ID parameter and also a value of the type. I'm defining here that, okay, owning a value of box T means that I have the points to chunk, the resource for the field. I also have the alloc block, which basically same as the alloc block we saw earlier. But we said that Roosevelt gives us the interpretation for all of the types, and this generic type has also its own interpretation. And we use this to say that, okay, this value that the points to chunk points to here satisfies the meaning of owning an exclusive value of T. So to wrap it, to review it briefly, the points to chunk to a value which satisfies owning exclusively a value of type T, and the alloc block, which basically tells us that this has been allocated in heap and also is needed later for the for dropping the allocation. Okay, let's go ahead. So if we just give this interpretation on and go ahead, basically we need to show that this starting from the new function, we need to show that. Sorry, I see a question. So, do crash if the user doesn't define proof obligations? Like, no, actually, I will show it. It will come up that the VeriFast will ask you to add them. Okay, so if we go ahead and start from the first method, what VeriFast does is that it generates the interpretation of this signature. So as you can see, we don't need to write them here. These are comments, but for users' convenience, you can also write them, and then VeriFast checks it about the Roosevelt interpretation of this type. Okay, so we again allocate using the global allocator. Again, we check that the size is not 0, following the discussion we had earlier, and checking for P if it's null. We saw that we need to change the bunch of bytes back to a point to chunk. Here is the same. So then we have the proper points to chunk, and then we get the points to chunk, which allows us to write on the memory which P points to. Then we put this pointer into the box, and you want to return box. Here it complains that you didn't provide the owning or the meaning of owning component of a box T. Why it does ask this in the ensures clause because the return type of this method is an owner of a box T type. It's not a reference. So then the interpretation of this would be the own component of box. And here is an example that VeriFast couldn't automatically close it. So I should close it manually here. And then we are good to go. Another one detail in this contract is that we see the thread token. This thread token is passing through all of the function calls in a thread. So it says that you are in thread T. And later in some thread local examples, we get to use it. So let's move on to the other.
I have some question, if that's okay.
Yes, sure.
So first of all, that's cool. I recognize some of this. So if I define an own type that comes, or an own predicate, that comes with a bunch of obligations. Like, for example, in this case, the box type is covariant. And so I would also have to prove that the interpretation of the box type is covariant interpretation of T. Box type is also send if T is send, and so you have to prove.
Yep.
Like there's a bunch of proof obligations that depend on various details about the type. Are you able to automatically kind of require those proof obligations, or how does this work currently?
We will get to that in a moment.
Okay.
If it's not urgent.
Okay. No,
Yeah, sure.
that's good.
Thank you. Very well. So let's go ahead. We get we are going to also verify drop here again. I have written these the contract for showing, and also user might want also look at the contract and do the proof in the body, but you can just align it and the VeriFast generates. So VeriFast checks this contract that I have written with the generated contract, which is the Rustbelt interpretation of this interface. So again, we are in thread T, because this time we are receiving a mutable reference. Basically, we should get something called a full borrow, but here we generate in a slightly different contracts from what Rustbelt says, and that is because we know we know about parts of the drop glue that compiler generates. So we are generating not the full borrow of this, but the full borrow content. What is the full borrow content? Full borrow content is basically a point to chunk to a value and the own predicate of that value. Meaning that so for example here, the full borrow content of the box T means that the self points to points to a chunk which there is a value stored there, and that value satisfies box T. And then we should destroy the box on and just give the chunks of box back. Let's see it in action. So box drop. Very well. I start from the beginning. What did I draw? So again, it produces, as we see in the unsafe example, it produces the requirement clause. We see that we get the thread token, we get the full borrow content of this box T, and we start to the body. I should open this full bar content. So as I said, the full bar content of a type means that we have the own for the value, and we have the points to chunk that self basically the points to chunk of the field which itself points to, or the field pointer. And then if we open the own predicate of box.t, which we ourselves defined earlier, so this full bar content is automatically defined, but the own predicate inside it is defined by us, which we defined it here. If I open it again, I will get basically its definition, its body. I get the inner points to that points to the value of t, and also the own component of t. So no, earlier we saw that in the unsafe example we didn't drop v. Here, because we have the meaning of having exclusive owning a value of t exclusively, and also its points to chunk, we can close the full bar content for t. Again, full bar content is a point to chunk to a value and the own predicate of the type. So we can close full bar content for t this time, which is needed for drop in place. So drop in place, when we see the call to drop in place, and in this upper section, we can see actually its counteract while we are calling it. It needs to, like other methods, it needs the thread token. We said that it goes through all of the calls, and then it needs the full bar content of the T, and then it gives back the thread token, then it returns, and then it just gives us the points to chunk, and the meaning of owning exclusively the value has been destroyed. So this destroys the own predicate of T, and then again, like the unsafe examples, we turn the points to chunk to an array of bytes, which then the allocation destroys it for us. And then we can, so basically drop also. This is all interesting stuff about the drop. Now we are trying to verify the reference. Here the input of the input parameter is basically here in the input parameter is a shared reference, and to have the give a shared reference to the internal value.
There's a question from Sasha. I don't know if you saw.
I'm curious why your precondition of drop is not the full borrow, but is content only. Since the function is safe, it should receive. So basically,
Ralph says that it's not a safe function.
No, actually, it's basically our justification is that so in Roswell there is no automatically generated drop, right? So here, if I find it, here I'm basically saying if we what does the compiler do? The compiler basically the drop that actually compiler generates gives the whole value and drops that. So after the drop that compiler has generated, this chunk will also be dropped. So what we are thinking is that the compiler generates a drop that gets the whole value, give you a mutable reference, and asks you to destroy the meaning of owning of this value, but give the chunks back. So we would always need to open this. So it would be always the case that we need to, if it was the full borrow, we would always need to open this full borrow, and then afterward close it. And then we couldn't, because we destroyed the own. So we are basically just justifying it, and by knowing that we are getting access to this full borrow content, and we don't need to return it back, because we know that that value which was borrowed and gave to us will not be used afterward. The compiler just drops the chunks, and that's it.
I mean,
hope
the
I
short
could
answer is
explain.
that drop is not a safe function, right? Like you can't actually call drop. If you try to call drop directly from the drop trait, there's a special magic check in the compiler which tells you can't do this. And it would be unsound if you could call drop, because it destroys the box. Any normal function which takes a mutable reference is not allowed to do this. Drop is a very special magic function that's only called in very particular circumstances. So it has a very particular specification.
Yeah. Thank you.
Just by the way, Nima, we have a little bit more than 5 minutes left, so I don't know if how you want to do things,
actually,
but it might be good.
I'm really close to end, because
Okay.
I'm just going to show the shared references and then sequencing. So here, if we would try to the reference, if we try to verify this dereference method, as the interpretation of the signature, we get another component of the interpretation of type T, which is its share component. And here it is only true, which means it's nothing in it. And it's auto-generated because we didn't define it earlier. So when you don't define the share component, VeriFast defines one that its body just true. So then the proof obligations are trivial for that. So then we don't ask the proof obligations in that case. But here, if I define this shared component, which specifies what does it mean to share a value of this type, then it will be proof obligations will be asked by VeriFast. So here I'm basically specifying this share component using fracture borrows. Fracture borrows representing are taken from Russell, representing like shared and read-only access as long as the lifetime that they are having as the argument is alive. Now that we define this the shared predicate, VeriFast says that okay, you have proof obligations to show. We should provide this lemma box share mono, saying that the share predicate that you have defined is monotonic related to lifetime. So if the lifetime is included in another, and you get the share predicate for the bigger lifetime, you should be able to derive the share predicate with the smaller lifetime. The proof is trivial because there are some lemmas in Rustbelt that says that fractured borrows are monotonic themselves, so you can shorten their lifetimes, and also the T itself. So we have also the meaning of share predicate of T in our definition of box T share, and T itself is share. So another again, because T is itself is a type, this monotonicity lemma also holds for T. We can use that to shorten the T share lifetime here, and that makes that's it about this lemma. Another proof obligation that arises is that you should basically show that given that you have a full borrow content of your type, you can share that and get your defined shared predicate. I'm not going to dig into the proof of this because it's quite long, and also it's mostly similar to Roosevelt. The examples are also available online. And with that, we get to open the definition of this shared predicate, and also justify this access. And remember that we had this the meaning of sharing of this sharing of T. So then also we can justify the return, the shared reference that the shared reference that deref returns. It also it also verifies. The deref mute is basically saying that if you get a full borrow of the box, you can give back a full borrow access, a mutable reference access back. Its proof is very similar to the proof of the share full lemma. So for the same reasons that I didn't show it here, I do not show this one as well. The last thing that there was a question about is that, no, I want to say that, okay, if, for example, T is sync, if T is sync, then box T is as well sync. So because we claimed this, then the VeriFast asks for this new proof obligation that says that you should prove that if you have the sharing predicate for box T, and also the T is sync, you should prove that this sharing predicate is independent of the thread identifier, so we can send it and use it in other threads. Notice
And
that
so
if
what if I don't have an impl? Like there's an auto impl for sync, right? Where my type is automatically sync if all fields are sync.
yeah,
Do you
but
support,
in
do you
that
support
case, you
that?
also get in that case you also get you will also get asked for the obligation, because it's
So how does
being
I'm curious, how does that work? Do you get the info from the Rust compiler, or do you like
yes,
re-implement
yes.
the entire trade
No, no,
logic,
no,
or
no,
how does
no,
this
no.
work?
We just get the info out of the compiler.
Okay, that's cool.
And then, yeah, so notice that here, if I remove the syncness of T, I will not get this fact about T in my contract of lemma. So it's also generated from here. And in the, yeah, we didn't prove this.
Okay.
And in
We're
the,
gonna have to sort of bring things to a close. I'm sorry. So
yeah,
if you have any
sure,
sort of
because
final
I'm done.
remarks, we can, yeah, okay. Well, then maybe we can still take a few minutes to see if there's any
Yeah.
questions. Yeah.
And I was just about to say that, yeah, we use this fact here as well to prove this thingness. So we show that we show this safe abstraction. There are more examples in the GitHub. like Cell and Mutex and Arc and RC. Those are using other different kinds of borrows and invariants. They are all axiomatized from Rust-Belt as well, but feel free to go and check them out, and also feel free to reach us if you had more questions.
Okay.
Thank you.
So Ralph, yeah, thank you very much. Ralph, I think you have a question.
I already had a bunch, so I would let others
Yeah.
go first.
Does anybody else have a question currently? I think you can just go ahead and ask your question while everybody else thinks for a bit.
Okay. Yeah, so that's very cool. In particular, I like all the integration around the proof obligations for sync and stuff. I'm not quite sure. You didn't mention covariance yet, so I'm not sure if you've hooked that one up. That's kind of one of the more subtle ones. But
No, we haven't.
yeah, you haven't? Okay. Well, to-do item, I guess. That's the most tricky one because I think it's not even shown in Rust doc. I have no idea how we'll even get the info from the compiler. But no, what my question was going to be is, so when you define an own predicate like this is a higher order predicate, right? Because you're defining
Yes.
it generically over any t, which is itself an own thing. And then you're stating these lemmata here, and these are very higher order lemmata because they're quantifying over an arbitrary t and its own predicate. So like the underlying theory here like fully supports higher order logic. Does this all like work out, or is there like, I don't know,
Sorry,
some
can
quirk
you
somewhere you
repeat
run into?
I think I lost you after you said that yeah, basically like borrows are higher order, and
So, but Ralph, I sketched. We have an informal soundness argument for this, and actually, I mean, some things are formalized in various papers. It's definitely not as foundation. I mean, it's not foundational. It's not as well proven as Rust-Belt is, of course. But we have some arguments for why this might be sound.
Okay, so I guess work in progress there to an extent. But that's good. I'm particularly wondering what happens if I do something like, I mean, I can define a type T where like T is equal to box T, right? Like I take a fixed point with box in the middle, and box is my user-defined type. And now I can start doing fun recursive things. Like actually getting the proofs for this all worked out in Rust-Belt was really, really hard. So I'm curious if there's any artifacts that show up when you do this kind of stuff in a system that is like maybe not prepared for all the higher order nastiness.
Yeah, so we tend to first axiomize things and then think about whether the axioms are sound. So we take the other route.
Yeah, well, that's why I'm probing them.
yeah, basically we did, and we just did some testing in our mind about some probable scenarios of unsoundness, and the best I have to say is that yeah, we couldn't show an unsoundness, but also we didn't prove anything.
Okay, thanks. But anyway, very cool stuff.
Thank you. Any other questions?
Any other? If not, then I'll invite any further questions to be held over Zulip. This is, as Sasha just said, very, very cool work. I'm looking forward to you guys continuing this and seeing where you can take it. Otherwise, the recording will be online soon, and I'll see everybody else again in November. All
Yep.
right.
Thank you, Xavier, for
Thank you so much,
organizing
Nemo.
this.
Yeah.
You're very welcome. I will also push the examples to the repo, so if somebody
Terrific.
wanted to
Yes.
play with them.
Perfect.